Hi everyone. This is the Calculus 6.2 notes, volumes of solids using discs and washers. I'm going to explain to you what we're doing in this section before I start the notes. I just want you to imagine the line y equals x, just the line y equals x. Okay, from 0 to 1, I want you to draw a line down to the x-axis. And I want you to take this region right here and literally rotate it as if it's a piece of paper. It's a flap of paper that you can rotate around the x-axis. That would form a solid. It would look like this. In fact, it has a name. It would look like a cone. And so we can find the volume of this cone, okay, by taking cross sections, okay, which have widths, basically. So we call these cross sections. These are called discs because these discs kind of look like a tuna can or a hockey puck if you think about it, okay? Each disc has a radius and each disc has a height. And the volume of a disc is pi r squared h. Now I use the word disc, but it's really a cylinder. That's what we call it in math. Pi r squared h is the volume of a cylinder. And so each of these little discs, if you pile them next to each other, okay, like that, so a disc here and a disc here, each of them has a volume. If you add all of them up, you'll get an approximate for the volume of this cone. The skinnier they get, right, the skinnier they get, they just look like round pieces of paper, the more accurate the volume of the cone will be. So I want you to look at this disc and this one. It's basically this disc flipped onto its side. The h in the problem is going to be this, and that's going to be our delta x, which is going to become the dx in our integral, okay? So keep in mind the way we find the volume of solids by rotating a shape around an axis, whether it's the x-axis or the y-axis, is by adding up infinitely many discs. And if you have infinitely many discs, the height or the delta x in the problem is just going to become so narrow that it's going to become an integral. The limit of the limit of the widths of those, it's going to become dx in the problem. And remember, the integral sign stands for sum of. And so in here is going to go a formula, and I'm going to show you that formula. So the volume of a solid using the disc or the washer method, I'll explain each of those, is going to be found either by, if we're using a disc integral, there's going to be a pi multiplier in front because of the pi r squared h. Pi r squared dx is really going to be our h, and then it's going to have some bounds, and I'll show you how to find those too. Or if we're using a washer method, again, I'm going to explain all of this, it's going to be pi some bounds, lower and upper, and then it's going to be outer radius squared minus inner radius squared dx. Okay, so capital R means outer radius. Lowercase r means inner radius, just so you know. Okay, so larger radius minus smaller. A disc is basically a circle that doesn't have a hole in it. A washer has a hole in it. So how do you get the area of a washer? You would do the bigger circle minus the smaller circle. So pi big radius squared minus pi little radius squared, right, is the area of a circle. Okay, so the best way to learn these is to do examples. Here we go. It says find the volume of the following solid. Y equals rad x rotated about the x-axis from 0 to 1. So first you have to draw. Let's get the graph y equals rad x on our paper. And we all know that that's just the square root graph. So this is y equals rad x. It goes from 0 to 1. So drop a vertical down. And then you're going to take this flap, this piece of paper, imagine. Okay, this is like a piece of string, and you're just going to flick it, and it's going to start rotating. It says rotated about the x-axis. This is the x-axis. It's going to form a solid, and it's going to look like this. When I look at it, I see like a Thanksgiving ham. It looks like a ham, okay? And so we want the volume of this thing. There is no set formula. But volume equals, now this is going to be the disk method because there is no empty space in the middle of this. I'm not going to have to subtract anything out. This is one solid, one piece, right? And any cross section in here, any cross section is going to be a circle. If you take your knife and you slice this ham and you open it up, you're going to see a circle. Whether you do it here or here or here, the cross sections are going to be circles, which is why it says pi r squared for our formula. Pi r squared is the area of a circle. The dx is the width of that disk we're talking about. And so for us, whichever axis you are rotating around tells you whether the problem is going to be the dx or a dy. If I'm rotating around the x-axis, it's going to be a dx problem. If I rotate around the y-axis, it's going to be a dy problem. And so my bounds have to go from x to x. It looks like, if you look at the region being rotated, that's what you look at for your bounds, okay? This is the region being rotated right here. The bounds are 0 to 1, so 0 to 1. I will have a pi in front, multiplier, pi r squared, and I'm going to have to find the radius of this cross section. And so if I take, the one I drew here, any random cross section in there, the radius will always be drawn. Let me note. Draw the radius, I'm going to capitalize this, starting from the axis of rotation, that would be the x-axis, to the original curve. Okay, so this is not the original curve. This is the original curve. So the radius looks like this. This is my r. And so I have to square that. See, that's what the formula says. So what is that? That is rad x. It says y equals rad x. This length here is rad x. So then you do the math. You say pi integral 0 to 1 rad x squared is simply x dx. And then you do your antiderivative work. What's the antiderivative of x? It's x squared over 2, evaluated between 0 and 1. I realize there's going to be a times pi in front of it. Let me do FTC. Plug in a 1, I'll get a half, minus plug in a 0, I'll get 0, which is 1/2. There was a pi in front of it all. And so 1/2 pi is going to be the volume of this solid. Let's do another one. It says, find the volume of the solid obtained by rotating the region bounded by y equals x cubed. So we have to draw this. Let's draw y equals x cubed. So y equals x cubed. Y equals x cubed. Y equals 8, which by the way is this horizontal line. This is y equals 8. And x equals 0. This is x equals 0. So the region we are looking at is right here, about the y-axis. So now we are rotating around the y-axis, which means our problem is going to be a dy problem. And so when I go volume equals integral, there's always going to be a pi in front. I'm following this formula at the top. It's going to be a dy problem, which means my bounds have to be y to y. So how do I get the bounds? I look at the region I am rotating. What's the lowest y? 0. What's the highest y? 8. Over here, I have to do r squared, radius squared. Remember how to draw the radius. You start from the axis of rotation. Put your pencil on the axis of rotation. The axis of rotation is the y-axis. To the original curve. This is the curve. So you draw your radius like so. That's the radius. In fact, when you rotate this shape, you'll get another ham. Actually, you're going to get another ham. It's just upright. And so the cross section is going to look like this. We want the radius of that cross section. So what is it? It's clearly the curve, but I can't just put x cubed here because this is a dy problem. So I have to go over here and solve for x. X is going to equal the cube root of y. And that is what's going to go in here. Then you start solving. Pi integral 0 to 8. This is y to the 2/3 power dy. What's the antiderivative of y to the 2/3? It's y to the 5/3 with a 3/5 in front. We're going to evaluate between 0 and 8. let me put the times pi in front so I don't forget it in the end. Then you FTC, you plug in the 8. 8 to the 5/3 power minus, then you've got the 0. And it's all going to be times pi. So this one is going to be cube root of 8 is 2 to the 5th is 32 times 3 is 96 over 5 minus 0. So 96 over 5 pi is the answer. Let's do another one. It says find the volume of the solid formed by rotating y equals 3x. So y equals 3x looks like that. It's just a straight line. About the x-axis from 2 to 5. So from 2, draw vertical, to 5. So the region we are rotating is not the full triangle. We are only rotating this much. What are we rotating around? About the x-axis, which means our problem is going to be a dx problem. We're rotating like so. And so what's it going to look like as a solid? I kind of see it as a lampshade, to be honest with you. It looks like it's going to be a lampshade, but it's going to be filled in. It's going to be solid. There's no empty space. So volume will equal pi integral. This is a dx problem because of which axis we are rotating around. We're going to go x to x, so 2 to 5. It's the bounds of the region you're rotating, 2 to 5. We have radius squared. Okay, so the radius is actually going to start from the axis of rotation, which is the x-axis. It's going to go to the original curve. This is the curve, so like so. This is our r. What is that? It's the curve 3x. And so you start solving. You've got pi integral 2 to 5. 3x quantity squared is 9x squared dx. You anti-derive 9x squared and you get 3x to the 3rd power. And then, you crunch your numbers. You get pi. Let's do FTC. Plug in a 5. 5 cubed is 125 times 3 is, I believe, 375. Minus 2 cubed is 8 times 3 is 24. So this is what? 351 pi is the answer to the volume of this solid. Okay, so for the next few, I'm not going to be solving. We'll just set up, okay? It says, take this region R, this region, this is R, okay? And rotate in a bunch of ways. So let me write down volume is either pi, little r squared, it's either dx or dy, I don't know. Or it's going to be pi, outer radius squared minus inner radius squared, and it's either dx or dy, right? So first of all, we're going to rotate about the x-axis. So I'm going to redraw this picture. Okay, this is 1. This is y equals x squared. If we are rotating around the x-axis, then it's going to look like, I don't know, kind of like a horn, the end of a tuba, I don't know. But it's going to be solid, right? So the radius is going to be drawn from the axis of rotation to the curve. This is r, which is just x squared. So volume will equal pi. This is a dx problem because which axis we're rotating about? We're rotating about the x-axis, so it's a dx problem, which means our bounds are going to be x to x, 0 to 1, radius squared. So the radius is going to be x squared. And I'm going to leave it like that because we're just setting it up. And then if I wanted you to solve, of course, you would FTC, et cetera, et cetera. But this is the setup. Now, so this was a disk. This is going to be our first washer problem out of the notes. So pay attention. What makes something a washer? Let me draw this region over here. This is a 1. This is a 1. It says rotate this region, the same region in the picture, about the line y equals 2. Well, the line y equals 2, you guys, is here. This is the line y equals 2. We are rotating around this line. So you have to take this shape here and rotate. So what you're going to have is this picture. Okay? Empty space. Empty space. it's kind of like this cylinder with a bowl carved out of it. So it's, you know, if I were to flip it on its side and pour water into it, it would not hold. This is empty. There is nothing here. It's just the outer wall, okay? Kind of looks like, if you do this, like a stadium full of people where this is the football field and these are the seats, okay? And it's the stadium is circular. So that's, I don't know what else to call it. That's what I think of when I see that picture. Okay, so then because of the empty space, it's going to be a washer. Volume will equal pi. It'll be outer radius squared minus inner radius squared d what? Well, I know I'm not rotating around the x-axis or the y-axis, but the line y equals 2 is horizontal like the x-axis, okay? So if you're rotating horizontally, this is a dx problem. All right, how do you draw your two radii? You always, again, every single time, start from the axis of rotation, which is y equals 2. Start there. You're going to draw two radii. You have to go to the original curve. So I go and I stop. That's my first radius. My other radius also starts from the axis of rotation, but it goes to the outer wall. So the longer one is my big radius, the outer radius. My shorter one is this inner radius. So how long is the outer radius? It's from this line to this line. It is 2. Outer radius squared. It is 2 units long. The shorter radius is definitely the trickier one. How do you get an expression for this shorter length? Well, if I went all the way down to the x-axis, it would be 2. But I have to take this piece out. What is this piece? This tiny little piece? It's x squared. So the shorter radius is 2 minus x squared. It's this length minus this much, which is x squared. That's the setup for that one. Now let's do another one where we rotate about the line y equals -3. So let's redraw. I'm going to draw my the region up here. This is the region we are rotating around 1, 2, y equals -3 is down here. Y equals -3, that's our rotation. So think about taking this and rotating. You're going to get a picture that looks like this. I'm not sure what this is. I can't think of a real life example for this shape, for this solid. It is a ring. It's definitely a ring with empty space inside. Okay. How do you draw the two radii? You start from the axis of rotation. You draw one curve, and then you draw the other one to the outer curve. So we need expressions for both. Volume is going to be pi. Now, is this a dx or a dy problem? Look at the axis of rotation. It looks like the x-axis, so dx. We're going to go 0 to 1 because those are the bounds in the x direction. Okay, now we need outer radius squared minus inner radius squared. So the outer radius, this much, only this tiny piece is x squared because it goes to the curve. But there is an additional 3 units. So it's going to be x squared plus 3. Top minus bottom, x squared minus -3. There you go. That top minus bottom is back again. What is the inner radius, the shorter one? It's just 3 units. So 3 squared. And then we'll do one more. It says, take the region, again, same region, the y equals x squared region. Rotate, oh no, this is a different one. It says, rotate the region bounded by y equals x and x squared. So let's not do that. Let's redraw. So y equals x squared and y equals x. This crescent looking shape, we're going to rotate that about the line y equals -1. Y equals -1 is here. Sorry, not y, x equals -1. I'm seeing it but saying it incorrectly. So we are rotating around x equals -1 this way. You know, let's see if I can draw what this solid would look like. This solid would definitely have empty space, an empty space. So it would kind of look like a bowl without a bottom. It would be, oh my gosh, you know what this looks like? It looks like an onion ring. That's literally what this shape is, you guys. An onion ring. We're going to find the volume of this onion ring. Yummy. Okay, now volume is going to be pi. It's going to be outer radius squared minus inner radius squared. Is it dy or dx? Well, look at the axis of rotation. Does it not look like the y-axis because it's vertical? So this is a dy problem. Okay, dy problem, which means our bounds have to go y to what? You look at your original shape that you're rotating. This is the original. What are the bounds in the y direction? They are 0 to 1. That's where the parabola and the line would intersect. So 0 to 1. Now, how do you draw your two radii? You must always draw them. You start from the axis of rotation, this one, and you go to the original curve. So you go 1, that's one of the radii, and then you start at the axis again, and you go to the other curve. Now you have to come up with expressions for those. So what's the longer one? The longer one, okay, from here to here would be just the curve, but then you have to add in a 1. But the problem is it's a dy problem, so we don't want to leave it as y equals x squared. We want to write it as x equals rad y. So this curve is x equals rad y. And so the length of the longer radius would be rad y plus 1 unit. Rad y plus 1 unit. It's going to be quantity squared. Minus, what's the expression for the shorter radius? Well, what's that piece? It's either going to be x or it's going to be y. This is a dy problem, so this is y plus 1 unit here. Y plus 1 quantity squared. Also, right minus left. Y minus -1 is that. And that's the end of the note. That's how you find volumes of solids where it took a shape and rotated around either the x or the y-axis.